Emma, the floor is all yours.
Great, thank you, Gerald. I appreciate the opportunity to be here for this session of It's Money. I'm going to be presenting on instrumentation and piezometer field testing during Wick drain ground improvement installations. And to be honest, in this particular project that I'll be including in this presentation, we didn't save any money. We, in fact, spent more money than we would have otherwise, but all in pursuit of the data that would allow us to consider future projects differently and more efficiently. So before I jump right into it, I wanted to first just do a quick outline of my presentation today. First, I wanted to start out taking a quick look at Wick drain ground improvement projects, that Wick drain methodology, and then dive into the common instrumentation requirements and methodology that we see on these types of projects. From there, we'll head to a case study in North Haven, Connecticut, where we were able to do 2 different types of installations for piezometers to compare the different methods and the data collected. We'll take a look at that data, and then from there, our lessons learned and our takeaway from that project and from that comparative installation study. So we've been involved in quite a few ground improvement projects over the years, and seemingly an increasing amount in the past few years. And like any project, as these come up, you tend to think what we can do to be more efficient, what advances can we make. And for us, we're talking about what we can do to provide the best data to our clients. And these images here are a couple of our projects from across the country in the last year. These projects start with Wick drains. So most of you are probably familiar with the methodology there. Wick drains, also known as prefabricated vertical drains, are a geotextile filter-wrapped plastic channel, molded strips that are put into the ground to provide a drainage path to allow for pore water to come out of soft compressible soils, allowing for an increased rate of consolidation. We have a quick animation here to see that in action, a mandrel installing Wick drains to design depth on a ground improvement project. Now, from an instrumentation perspective, which is how I approach all of these, we see a few different systems being included in project requirements. The most common are really these first 2, sediment plates and piezometers. Sediment plates are put into place to get sediment data of the native soils during this process. They can be read by automated motorized total stations or manual survey. They're a relatively inexpensive system, easy to install and provide really reliable data. Piezometers often go hand in hand on projects with sediment plates. These are providing accurate data on pore pressure. They take a little bit more of a nuanced installation, but also relatively inexpensive. Some other systems that we do see include settlement cells and horizontal inclinometers. Both of those systems are a little bit more involved in terms of installation, a little bit more of an expense in terms of initial hardware and sensor purchase, but also provide great data if the application is there for them. We also see projects like this requiring vibration, noise, and dust monitoring. And this isn't so much because of the Wick drain ground improvement methodology, but just because of any project site in close proximity to a residential, commercial area or to infrastructure might require those. But where I'm going to focus today is sediment plates and piezometers, really about the piezometers. So sediment plates, to give a little bit more on those, we have some examples here, some typical configurations. These often start with a 2x2 base and a riser. Additional risers are added with the progression of the work to get above that level of fill or surcharge that is being placed on the project site. Optical prisms, as you see in a few of these configurations, are included at the top of the riser to be able to integrate these with an an automated motorized total station, so it can read those optical points. The AMTS system is set up on site to be able to provide the readings of the settlement monitoring points. So it's first most important to find a location that can see or have a good line of sight to all the settlement monitoring points. In this picture, which is actually from our case study later, we had an advantage of having a nice high point on the edge of site, which gave us a good line of sight across to all of the settlement plates. This provided hourly readings of each one of those prismatic targets, giving us an XYZ value. Really here, we're only looking for settlement. It's only that Z measurement that we're taking away. The system itself is typically solar powered, and using cellular communication will actually take that data collected and send it back to a server or a web platform. This system also allows for an easy update to be made when risers are added to those settlement rods to extend with the progression of fill placement and the work on the site. Now, piezometers. So this is kind of, in my view, one of the more exciting things, exciting sensors. I'm a fan of them. These are sensors that provide pore pressure measurements. Typically, we see them as a vibrating wire type sensor, meaning the operation of the sensor is a tension wire that, when subjected to an excitation, kind of plucked like a guitar string, will have a reading, a frequency reading that can be understood, calculated to a pressure or PSI value. The ranges of sensors that we typically use in these applications are either 25 or 50 PSI. Now, piezometer automation. There's been, quite a few ways to read these, to automate these, that we've done, that I have done over the years. The one that we have here, the one that I'm focusing on, is using a mesh network. This allows for us to connect each one of these sensors or a tight cluster of sensors to a node that will take readings every 30 minutes. In this type of setup, the nodes are attached to the risers that protect that signal cable that are risen, just like settlement plates, through the fill to the surface. This allows us to minimize cable runs and the potential for cable damage during the course of the project, and provides us with those great 30-minute readings for each one of the sensors along the way. These nodes actually are powered by internal batteries. So at a 30-minute reading frequency, they can go for about 10 years. So over, a 6-month grant improvement project, we have no issue with those individual nodes and their power consumption. These then communicate through an on-site cellular gateway, in this case located, right by the total station, good line of sight to all the areas, which then can transmit to a web platform. So now we can head to North Haven, Connecticut, and get into a little bit more detail about putting these piezometers and even this AMTS into practice on this recent project. So the Valley Service Road extension, located in North Haven, Connecticut, this was one of those types of projects that when we first went to site, we were told to drive until you're sure you're lost and then go another 2 miles. The service road extension was going to connect this roadway, this Valley Service Road, to a roadway at the back of a nearby distribution center, which would allow for easier access for the distribution center to the Highway 91 that was close by, and alleviate local traffic congestion. So from where it started, which is the picture we see here, to where it was when I went to visit that site and take this picture last week, quite a bit of change. So at the point we came into the project, wick drains and instrumentation were required at the existing grade as part of the overall ground improvement process. The overall grade of the project site would be significantly higher at the end of the project to accommodate for this extension to meet with the roadway at the distribution center side, which was significantly higher than the existing grade. The instrumentation requirements per the specifications on the project were for 6 settlement plates with 5-foot risers to be added with progression of the work, and also for piezometers. These would be located in 4 spots along the project, and each location was actually going to be including 2 sensors, 2 separate boreholes at elevation -20 and -40. The required reading frequency here was weekly. As I'll describe later, we approached this with an automated system, which provided more frequent readings and a little bit more of a fine-tuned view of the data coming in off the project site. So here's a view of that project layout, a little crooked as I stitched it together to get a good view. So you can see actually the earlier photos I showed were taken from the left-hand side, looking up towards the distribution center area. You can see that they have the 6 settlement plates there as those red boxes, and then the 4 clusters with 8 total sensors for the vibrating wire piezometers. Now, the AMTS system, so you've already seen this image here on the left, was installed at that distribution center end of the project. So it had the highest elevation, good line of sight to all our monitoring points. It also had good solar exposure for power considerations over a project of this duration, something along the lines of 5-6 months. It's important to make sure that the power consideration can overcome the weather you might experience over that time, or just a couple of cloudy days. It was mounted on a beam driven by the GC on the project into the ground there to give it a little extra height and allow us to mount those communications and power peripherals right onto the beam. All of the settlement plates, you can see a few examples there. On the right-hand side, had that optical prism on the top of the riser, and it was adjusted with the progression of work and the addition of more of those 5-foot risers. So the piezometer installation, the real excitement is here. Would we use traditional installation method or utilize the Wick drain rig itself, or would we do both? So on previous ground improvement projects, piezometers had actually been installed with the Wick drain mandrel. On that, we had no way to compare the data collected there to traditionally installed piezometers. But this project actually gave us that opportunity. So when we approached the project piezometers, we included the project specification units, 8 vibrating wire piezometers at those 4 locations with those 2 depths per location. And those would be done in a traditional method where we would have that 4-inch borehole, installing the sensor within a sand layer, sealing with bentonite chips, and grouting to the surface. And we would also be then installing a further 8 sensors to maximize our ability to compare the data values. So each one of those would be installed with the Wick drain rig, and to match both adjacent location and depth of the project installed units. So you might be wondering, how do we install a piezometer with a Wick drain rig? It's an understandable question to ask. But we start with the standard approach, saturating our sensor. And then we actually take a piece of the Wick drain itself. We're utilizing that as a geotextile sandbag. So we take out the plastic core and we're left with just the geotextile. We secure it with an anchor plate, which is typical to the Wick drain installation method. And then we actually fill that geotextile with the sensor in a sand pack, then a layer of the bentonite chips above that sand pack to ensure a seal. So here are some images of that piezometer installation with the Wick drain rig, a little bit of a close view. We have the piece of Wick with the sensor installed in that sand pack with an anchor plate on the left-hand side there. In the middle, we have the mandrel driving it to depth. And then we have what happens after the mandrel has been pulled out by the Wick rig. We have that signal cable coming up the hole to the surface, so then we can proceed to connect it to the automation, whether that be a traditional method or in this case, our vibrating wire nodes. So we proceeded with this method to install 8 of the comparative installation study units. So all 8 piezometers were installed with this method. As we went along, a few adjustments were made to kind of counter some things that we encountered as we progress, and I'll touch on those a little bit more later as we look at the data itself. The pattern we had for installation at each one of these clusters was done with respect to the already installed wick drains. You can see the layout they have here on the left, triangular pattern. So we roughly centered each piezometer within a triangle of those wick drains, having the two traditionally installed units side by side and the mandrel installed unit side by side in that next row. So the process that we went through with the traditional method for installing our piezometers, of course, that initial saturation of our sensor, we then packed into a geotextile sandbag with clean sand. We put that into the 4-inch borehole at depth within a sand layer. We had the bentonite chips above that sand layer to seal and then grouted to the surface. Again, that signal cable was run to the surface for connection to our automation system. Here's a couple vantage points of that part of the installation. With this approach, the time that was required to do this installation meant that the project team was kind of working around us to get their stone layer started and be ready to continue with the progression of the rest of the work on the ground improvement side. Now, with all 16 units installed, we completed the monitoring system installation with the mesh network and the node installation. So each one of the piezometers got a vibrating wire node that would collect at that 30-minute frequency we discussed earlier. The nodes were directly attached, to the conduit that actually was used to protect and run that signal cable up from the point of installation. This conduit was extended a few times during the project to match the progression of fill or surcharge placement. The node was raised on the conduit as that was extended further up. You can see here we have those roughly 4 locations for clusters of piezometers on the left-hand side. So during the course of the project, we created and maintained 2 different project websites. One was allow for the project team to view those traditionally installed piezometers and the settlement data as it came in to understand the progression of the work and when they reached their design parameters. The second site was developed as that research and development type platform for us to visualize the data coming in from all 16 piezometers and of course the settlement system as well. The website allowed for us not only to see the data as it was coming in, but also to keep an eye on system health. As with any instrumentation system, periodic maintenance was needed over that 5-month period to make sure communications were working well, to add risers, of course, and even at one point clear weeds that had grown up over one of our solar panels. New England in the summer can be notorious for wild weed growth. The piezometer data as it came into the project site was processed using the polynomial gauge factor as provided for the manufacturer. The data was also displayed in differential pressure readings with the temperature in Celsius. So with the data in hand, it was time for us to really see what it looked like and get to comparing the 2 methods. So we looked at the data in terms of clusters of instruments. We refer to them as clusters 1 through 4, as you can see going from this plan view from the left-hand side to the right-hand side. You can see the settlement data was there reporting underneath. So the data from all sensors, you can see actually in this graph, all sensors from cluster 1 there on the left showed corresponding increase in pressure from surcharge placement and subsequent dissipation. We also see that looking at, all of the sensors in one cluster, not only are they showing the same trends of the pressure increase and dissipation, but they're showing considerable data overlap. To get a little bit of a closer view at that data from those sensors, the pressure data specifically that we see on the bottom here, we decided to look at it in terms of the two sensors installed at the same depth, one in the traditional method and one with the Wick drain rig. You can see those there on the on the right-hand side. The top one, we have the two that were installed at the -20 elevation and below the -40 elevation. So considerable data overlap in those two graphs. Actually, between the two methods, the average difference in the PSI values was 0.05 over the 5 months, a maximum difference at 0.45 over that course of time. So one cluster data stood out with a little bit more difference than the others. We see here on the left-hand side, this is actually cluster 4, which included two sensors, of course, the traditional installed to the -40 and the mandrel installed to the -40 elevation, which showed us the same trends of pressure increase and dissipation, but had a significant difference. They didn't have that same overlap in data values that we had seen in the other clusters. So this is where we actually go back and look at the installation. So the initial sensor driven to depth that we saw here had been driven by the mandrel aiming at that -40 elevation. But as the mandrel was removed, that sensor actually anchored higher. It didn't stay at the depth that it was driven to. The difference in installation depth here was just over 9 feet, actually. So subsequently from this installation, we have made modifications to the installation after that sensor to help that anchor at depth, increasing the size of the anchor plate, and subsequent sensors, the one that we see with that data overlap, actually stayed within about 2 to 3 feet of one another in terms of the target depth of installation. So it was a good moment to learn from in terms of the potential for the depth not to be quite a target from that initial installation. So throughout this project, we saw the data coming in and were able to understand that the Wick drain mandrel installation provided reliable core pressure data on this application. Not dissimilar from the traditional method, we saw the same trends and we saw significant data overlap in units that were able to be installed at that same target depth at those different clusters. The installation of 8 sensors, 8 of the piezometers with our Wick drain mandrel was actually completed in 1 day. And that was involving the Keller Wick drain field team, the Geo-Instruments field team to get it done. It was completed in 1 day. It could potentially have been closer to about a half a day with the process a little bit more refined. The traditional installation of 8 sensors that was done with the local drilling team and the Geo-Instruments field team took 6 days for the 8 units. So in looking at the estimation of cost savings, not including the time that could be given back to the project team, the estimation was around the $35,000 mark. So not insignificant in terms of dollar amount that could be saved, and of course, time as well. But in terms of giving our team a little extra time in the field and the opportunity to crunch a little bit more data than usual, we would say that is priceless. So thanks for listening to the comparative field test of these piezometers and the instrumentation parameters of Wick drain ground improvement installations. And I look forward to any questions you have at the end.
Thanks, Emma. Thanks for this presentation.